even more now that with satellites that are producing petabytes of data, we have a great quantity of information that can be used to improve the current climate models using AI. But just knowing more about the climate dynamics is not sufficient. This is a human problem. The action of humans is the main factor, is one of the main factors in the speed of the climate change in the previous years. So it is very important that we understand and are able to model how humans behave in regards to this problem. Why we are not yet cooperating enough to solve this very serious issue. And data, acquiring data over this problem is very important, and I'm going to show several experiments that have done that, but also working on generative models that, without using data directly, are able to explain it. And I'm going to show both approaches today. So, as I said, the climate change is a very serious issue and very complex. And that's because we have many different countries with different ideologies and socio-political situations that have to cooperate. And they have to cooperate even though the possible benefits of investing on solving the climate problem now might only be collected in the future. And so very often, and that's what we've been seeing in the different climate summits, countries decide to wait and see what others are actually doing. But if everyone waits, we're never solving anything. So in order to be able to represent this collective risk scenario, it's a collective risk scenario because we have a very serious issue that may affect everyone, may have an impact on everyone. In order to be able to acquire data over this and model it, we represent it as in the following way, as a public good game, in which we have a group of participants that have some private money. That's what I represent by the circles and the numbers there. And we have a common pot. And throughout a certain number of rounds, these humans, these participants, have to invest in this common pot a certain number of actions, either 2, 0, 0, 2, or 4. And if by the end of the experiment they actually surpass a certain target, then everyone is happy. We solved the climate change. There's no more climate disaster happening. However, even in this case, you can see that not everyone has made the same effort. And this is represented by people ended up with different amounts. However, if they don't manage to reach the target, then a disaster might happen. And with a certain probability, a certain risk, everyone loses all their pockets. There's a climate disaster or the earth burns. And so this risk is only one of the uncertainties that are inherent to the climate change problem. And it's known in the literature as impact uncertainty. And it basically refers to the fact that we don't know for sure how the climate change will affect us. Will it affect everyone? The whole earth will crumble. Will it affect only the poor? We don't know that for sure. And actually, an experiment by Malinsky has shown that humans only start contributing to avoid the climate problem when the risk is very high. That's what you can see in the 90% case. There's a 90% probability that if you don't reach this target, everyone loses everything. And even in this case, only 50% of the groups analyzed in this experiment actually managed to avoid a climate disaster. And actually, if we look at what happened during the experiment, in the x-axis here, you can see what happened at every round, and in the y-axis, the accumulated contributions. You can see that even in the highest risk case, the 90% case, people only managed to reach the target at the end of the game, by the 10 rounds. The target was 120. This is what we call procrastination. They're waiting and only managed to do it at the end. But this impact uncertainty is only one of the types of uncertainty that surround this problem. There are others. For example, threshold uncertainty that refers to the fact that we are not certain about how much should we reduce the emissions of CO2 or how much should we avoid the temperature to increase, if it's by 1 degree, by 1.5, by 2. And this may seem trivial, but actually, it does affect what people do, how people behave. If you look at this experiment by Scott Barrett and Dannenberg, they analyzed what people do when there was a game with full certainty and another one with full uncertainty, with threshold uncertainty. It is not very important that you understand everything that happens in this graph, but in the x-axis, you can see what people donated during the game to avoid the climate problem, and in the y-axis, what they said before the game started that they would do. So in the case without uncertainty, where you see a lot of points together, it just means that people did exactly what they said they would do during the game. However, this behavior changed completely when they added some threshold uncertainty. And people actually started to use this initial communication as part of their strategy. Their behavior shifted. And this actually resulted in a lower success rate. If in the first case the success was very high, in the second case success decayed. So we are seeing already that uncertainties and the way information is transmitted has an effect on how people behave, on how people work. And what we did recently is that we wanted to understand what is the effect of time here. And what we call time in uncertainty is the fact that we are not certain about how much more time do we still have to avoid a climate disaster. How many years do we still have to prevent or to mitigate the climate change, anthropogenic climate change. And so we modeled this by making players not know when the game is going to finish. Now there's a certain probability, that's the only thing they know, that the game is going to finish at a certain round. And we did an experiment in this room with 246 participants. In the first treatment, we did an experiment very similar to the first one I showed you. There was no uncertainty. There was exactly 10 rounds, 6 participants, and people could donate 0, 2, or 4 units, and the target was 120. In the second experiment with low uncertainty, they only knew that the experiment would take at least 8 rounds. On average, 10 rounds, and after the 8th round, there was a probability of 1/3 that the game would end. Then we did a third experiment with a much higher uncertainty. There was a minimum of 6 rounds, and after that, there was a probability of 1/5 that the game would end at each round. In all the cases, the average number of rounds was always 10. And this is what they could see in their screen. They could see the amount in their pockets, the amount they still had, and what the other players in the group did in the previous round. And this was the result. When there was no uncertainty, we see something very similar to what happened in the first experiment, that people only managed to reach the target, this 120, by the last round, in 10 rounds. However, when we add a little bit of time in uncertainty, people start investing earlier. And they actually end up reaching the target much earlier, by the 8th round. But when we increase even more time in uncertainty, this effect disappears. And even though they still invest earlier, they do not increase their investments by the same factor. And actually, they no longer manage to reach the target earlier on average. So we already seen that there's some effect here. People invest earlier when there's some uncertainty about time. But we also observed that there was an increase in polarization. If you pay attention at the first bar, where there's no uncertainty, we call the people in the yellow part of the bar fair players. That's because they're investing exactly what we call a fair amount. And those are most of the players when there's no uncertainty. However, as we increase uncertainty, these players diminish in favor of the extremes. And we start seeing more players investing more and more players investing less. And this is very interesting, because this is what happens actually in reality. We see that in times of uncertainty, we start to see much more political polarization. But this is not the only thing. We can now not only use data, but we can use AI to understand how people actually behave. Why are they acting in a much more polarized manner? Why are they investing earlier? I don't know if anyone here has any idea of what would be the best strategy in this game. But what people did, there's a bit of a problem in this plot, but basically what we are plotting here on the x-axis is the donations of the group members, of the other group members in the previous round, and on the y-axis what each player did. So we're just showing the actions of the players in function of what the other players did. And we see already a difference here between what happened without uncertainty and with uncertainty. We see a difference in the slope of the fitting function. And we can see this even better if we look at the frequencies of each action with respect to the donations of the players, of the group members in the previous round. We see that when there is no uncertainty, most players are always playing too. They're doing that mostly unconditional to what others are doing. However, when we add time and uncertainty, and mostly we can see this even better in the case of high uncertainty, they're playing conditionally. What this graph is showing is that they start to only give more when the others are also giving. And this was, I'm only showing here the results of the successful groups, the groups that actually managed to reach a target. And basically this conditional strategy, this reciprocal strategy that is only donating when others are doing the same was the most successful in the case of time and uncertainty. And now what we did was we did some extra analysis over this data, and we managed to cluster it in around 5 behaviors. And we created a multi-agent game theoretical model to try to explain the dynamics among these 5 behaviors. Basically, the strategies were what we call fair, people that invest always 2, free riders, people that invest 0, altruists that invest 4, and then the conditional strategies we call compensators, the people that are only going to invest if others are not investing anymore, in order to still reach the target. They do not invest when others are investing. And we call reciprocals those that we just saw that are only investing more when the others are also doing the same. And what our model shows, so this is a Markov chain. It's not important that you understand this concept, only that in this network, the arrows show a relationship of dominance. And dominance in very rough terms would mean that if a strategy that is pointed by this arrow will play against the other strategy, it will win. And what we can see here is that there are mostly fair players, as we saw in the experiment, in the case of no uncertainty, and reciprocals are being dominated by compensators. However, when we add high uncertainty in the model, this arrow changes. And now reciprocals are starting to dominate compensators, and that's what we saw before. But there's a drawback. Now there's a new arrow coming from fair players to free riders. And what I didn't say to you before is that in the data we saw that when there's a very high time in uncertainty, success decreased. And we can see here that uncertainty is actually affecting, and fair become dominated now by free riders. And this is something that we want to affect, and that we want to avoid. And that's why it's very important to invest in AI to reduce as much as we can uncertainty in the climate models. So now, to conclude, I have talked to you about the role of uncertainty, mainly about time in uncertainty, and we saw that it leads to polarization. And also that successful behaviors are, in general, when there was high time in uncertainty, reciprocal behaviors. And taking this into account, if we go back to what I said at the beginning, that countries are always waiting to see what others are doing, if we say that the others are also playing this reciprocal behavior and everyone is waiting, then we're never going to solve the climate problem. And that's why it's very important that we start investing now, we start taking action as soon as possible so that we can incite and encourage reciprocation from our peers. And I don't know if there's some extra time still. I have an extra slide with some food for thought. I want to finish this presentation with a question. There's a new project that I'm working on that is related to this social AI. So now we can see that in most cases, people are not making decisions alone. When we go somewhere, usually we look at Google Maps to make our decision. So it is fair, there's a problem on this image, but if it's fair to say that we are already interacting in a society where there are artificial agents and humans, and the question that I'm trying to ask here is whether we can actually use these artificial agents to support people's decisions, to improve collective decision-making, to achieve more cooperation, maybe to get people to surpass the tipping point and actually take action to avoid the consequences of anthropogenic climate change. So these are the people that participated in this project. Thank you all for coming here.
Thank you very much. It was a very, very interesting talk. Question?
I have a small question. In your model, like all the players at the beginning, do they have the same amount of credit?
Here? Yeah. They always start with the same amount. There's different research, mainly theoretical, in where you have heterogeneity. They basically study what is the effect of having rich and poor, so people that start with less. And what they end up seeing in this case is that when there's a very high risk, rich invest more and play an action. But in reality, the perception of risk is different. And when the risk is low, in this case, when there is a difference in initial endowment, then nobody does anything and the system goes down.
Thank you.
Over there.
So thanks for the talk. I was wondering, because this is with, like, if I understood well, like individual players or something, but do you have data or not data, but conclusion from this kind of games, but with governments, like where you have other kinds of effects of like you have lobbies and stuff that can impact the results?
That's very interesting. No, I don't have data on that, but there is some research in what is the effect of electing representatives to actually make decisions for you in this context of the climate change. And they see the same thing, that, again, risk is a very important factor.
Thanks.
Last question, over there.
Did the participants on beforehand know that it was about climate change, or was it just a
in the first
random error?
I'm sorry. So yeah, in the first experiment I showed you, they did know that wasn't climate change. In our experiment, we did not say it. This makes our experiment valid for other things, and mainly takes out this factor of knowledge about climate, that in 20 years maybe it's very different and people would have done something else. So we do not tell participants anything about the climate change, just that the model itself represents, the game itself represents abstractly this problem.
Good.
Thank you. All right, thank you all.
So we will welcome now our last speaker, Olivier Martin from Tractable Engie.
Yes, that's the last one, so I can put it at the beginning. Okay, thank you very much. Do you hear me in the room? So I'm Olivier Martin. I'm head of data science at Tractable Advanced Analytics, which is a part of Engie. And I will try today to show you in the industry of the utilities how we see climate change and what we can do, what we're actually doing that use data science to try to improve the situation. So I start with a short question for the audience. For those who didn't see the answer when Philippe was going back up in the slides, do you have an idea of what this represents? Someone? Maybe a glass which is empty and you will drink something in 20 minutes, but you still have this presentation to listen. Maybe it's easier with this. Probably, I guess most of you I've already seen this kind of graph. It's not data science, it's more economics. It's the way it's the offer and demand curve. So basically you have a quantity that you are willing to buy, and the higher the price, the lower you will want to buy a big quantity. And the opposite, if you put a very high price, you will have a lot of people offering stuff, and then you will have a very high offering. And the intersect of the offer and demand curve is determining the price of the underlying. So why am I showing you all this? Because in the case of electricity markets, energy markets, it has a very specific shape, this kind of offer and demand curve. If you see on the y-axis the price, on the x-axis the quantity. First, the demand, it's the easiest part of the chart. The demand is quite vertical, meaning that in today's world, people use electricity and they don't care much about the price. You will not ask yourself, is it really worth it that I turn on my light now, or do I? We start to have some industries that sign contracts with utilities so that they accept to reduce the consumption when the electricity price is very high, or we start to think about maybe if there is a blackout coming, should we reduce our electricity to avoid this blackout? But basically the rule, to simplify it, is that it's quite vertical. You have a fixed demand. And then you have the different types of technology. Again, this is a very simplified chart. It's trying to put everything in picture. So when you have the renewables that are installed, that exist, it costs nothing to produce electricity. You have the wind is free, the sun is free, so you're just producing at zero cost. Then you have the nuclear assets that use a very cheap uranium. It's very cheap to produce. It's very expensive to build a nuclear power plant, but it's very cheap when it's already operating. And then you have the gas-fired power plants, and then the coal-fired power plants, and then the diesel generators, which are the most expensive to run. And the idea is that basically you will always use as much renewable energy as you have, because it's the cheapest. Then you will use the nuclear. Then you will use, if you need more, you will turn on the gas-fired power plants, and then if it's even not enough, you will start your coal power plants, and so on. And the more you go on the right, the more polluting energy it is on this chart, at least on carbon perspective. So why is it important? As you see, this is there are different sources probably, but this source says that the energy accounts for about almost a third of the CO2 emission in Europe. So it's very, very important to try to reduce, on average, the part of the gas, coal, and diesel fired power plants. So what is the first thing that we can do for this? Of course, we could increase renewables energy, or increase the part of renewable energy in the energy mix. So what we will do is if we increase the amount, the quantity of renewable energy, it's like if we will shift all the other technologies to the right. So the demand stays fixed, the rest of the technologies go to the right, so the amount of emissions that you will send back in the atmosphere will be reduced, because the amount of gas, coal, and fire power plants will be really reduced. But can you really increase renewable such easily? It's not something you can control. Sometimes there is wind, sometimes there is no wind. Sometimes there is some sun, but not in the night. And basically you do not have full control. So when I say we want to increase renewables, I say we want to increase their availability. So we want, when you have solar farms, we want that the efficiency is very high. So with the same sun, you put much more electricity into the grid. We want also to avoid windmills that are stopped because they're broken, because they need maintenance. So we want to reduce failure rate of the component. We want to make sure that the whole wind farms is running. And we want also to extend their lifetime as much as possible. Because of course, it's zero carbon when it's running, but it's costs a lot of carbon to produce solar energy or wind farms. And the last maybe point is, as I said, it's intermittent production. So when you have, for instance, a lot of sun, and then your solar panels are producing a lot of electricity, but suddenly you have a storm coming, and basically the solar production drops a lot, you need to turn on maybe a gas-fired power plants to provide the energy that you need, because the sun has dropped, the solar quantity has dropped a lot, and you need an alternative. And so if you can better predict what will be the renewable production, you are better able to adapt to what is coming and to tune your electricity sources so that you are more on a more ecological way of producing the electricity. You don't have to start in a diesel generator in emergency, because you will have you have the time to modulate the production, for instance, of gas-fired power plants. So this is the big picture. As I say, we want to increase the renewables, and I'm going in the wrong direction in my slide. Sorry. And what are we doing concretely? I took the example of solar. We are also very active in hydro or in wind energy, but these are typical applications that we are working on within Engie to try to improve things. Things like shading detection. In huge solar farms, you have the grass that is growing and sometimes covering up to 10 to 20% of the solar panels, and that is providing shade. So you lose a huge quantity of energy. Being able to detect when this shading starts to be harming your production is really useful, because you can then take action and prevent loss of production. You monitor the inverter efficiency. Maybe it's a bit complex to go into details. We also do a lot of work to use the data to detect when a degradation of the solar modules is happening faster than was planned by the manufacturer. And I will take a little bit of time to go a bit more in details in one of these applications, which is the soiling evaluation. And soiling is the accumulation of dust on solar panels. So it can be a very big issue in arid countries where there is a lot of solar installation, such as in the Middle East or in Africa, for instance. When you have dust covering the panels, and it can decrease the efficiency up to 50%. And of course, because the solar farms can be huge, it's very hard to go and manually check every day that each solar panels, what is the quantity that we observed, and should we clean the solar panels or not. So we have tried to see if we could provide a solution to this problem with a data-driven approach. And we first tried to really talk to the people working in the solar industry to understand the problem. And first, they explain us okay, that most of this dust accumulation is actually washed away by rain. So when you have high important rain falls, then it cleans the solar modules and it washes the dirt away. So you could see on this chart is the normalized production in green, and in red is the solar irradiance, and in blue you have the rain episode. So you see on the right part of the chart, you see that the green is higher, meaning that with the same quantity of sun, you produce more. That was quite obvious, but the longer there is no rain, the higher the dust accumulation, because of course the surrounding becomes dry and there is more and more dust that flies with the wind and that sets on the panels. So you see here again the green that decrease over the time as there is no rain episode coming, because actually you see the dust is accumulating and reducing the efficiency of the solar modules. There are other factors such as wind in some cases that can also blow away dust particles and other particularities, but these are two big effects. So we try to develop a data-driven approach to use this kind of observation. And what we did was an approach that used two machine learning models in parallel. One that used the traditional variables that you would use to forecast the solar production, such as the irradiance, the hour of the day, any kind of weather, basic weather data. And you would have a second model that would also, what I call here the model A, that would also incorporate soiling variables in its input variables. So in this model A, you would also add the number of days since the last rain, for instance, or the quantity of rains that was observed in the last 24 hours. And then you make the two machine learning models, do the training, and predict what would be the solar energy that would be produced. And you look at the prediction and the realized solar production. And then you look at the error of the two models. And actually, when the difference of the error is big between the two models, so when the model that has the so-called soiling variables in the input is able to much better predict that the model that does not have this information, that means that the soiling is an important factor into the solar production forecasting model. That means that by knowing that it didn't rain for a long time, or by knowing that it has rained a lot the last night, the model is able to better predict the solar production. That in this case there was a problem of soiling, because these are really the variables that we add to the second model had a great impact on the accuracy of the model. So with this kind of dual machine learning approach, you are really able to use machine learning to quantify the impact of a phenomenon by using variables that are linked to this impact. And it was an idea that we had, and we tested it on about 100 Mexican solar installation, and basically it worked quite well. I will not go to talk too much about the points on the upper right, because this is a bit specific, but for the others, you see that you have a relative evolution of the production after rains that is globally positive. So after rain, the solar modules are washed, and the production is higher. And then also you have the increase, or the increase of accuracy of the model that is higher when you take into account these soiling variables. So we applied it on a 100 Mexican solar installation. We validated the ID, and then now we are deploying this strategy on the whole Engie fleet in the world. So it's more than 1 gigawatt of solar farms, and we are getting the first results. But the idea behind this is that you would be able to quantify the amount of soiling that is present locally, and then you are able to optimize the cleaning program. So you know that you are getting 8 or 10% of soiling on your panels. You know it's time to clean your modules, and controversial if you see that it's still very low. You do not do unnecessary cleaning, and I said it's because it's very big quantities, very huge solar farms. It has a lot of impact, both in terms of production, but also economically. So there was one example. I wanted to go a little bit into details in one of these cases, but to illustrate a bit the kind of activity we have. But there is another, maybe another approach. Instead of trying to increase renewables, we also are very active in trying to decrease the demand. So it's the same effect actually. If you increase renewable, you would shift everything to the right. If you decrease demand, then you shift the demand to if you decrease demand, you shift the demand to the left, and so you also, of course, decrease a lot the amount of CO2 emissions that you emit. Then the first question is, why would a utility such Engie decrease the demand? Because it's actually a company that is selling electricity. So you would first probably think that it would be a stupid idea for a company such as Engie to try to decrease the demand, because they are making their profit by selling the energy. And it's actually it could actually be true, but it's true for Engie that we are at this stage making a big turn. Instead of having a business model which is based on getting the revenue by getting euros every megawatt hour that we are managed to sell to the clients, the world of energy is really shifting to a world when the energy is much cheaper, it's much more decentralized, and now the focus is on the service that is provided per megawatt hour that is sold. So Engie is today saying no to coal plants. They are selling or closing all the coal plants. They are really focusing on boosting the renewables quantity, and this 1st of July they are creating a new entity called Engie Impact. I will be part of this entity, and there is about 100 people within Belgium that will join this entity, whose goal is to drive the B2B clients and B2T clients toward a zero carbon transition. So really trying to advise big clients on how to be more go toward a zero carbon transition. So there's really this shift that is a strategic shift decided by Engie. We don't want to try to sell as much energy as possible. We want to indeed try to sell as much services to the client as we can. That's where we will differentiate from the competition. And maybe an example on how to do this in practice. For instance, we had about 3,000 clients that agreed to participate to a test case in which we had a smart thermostat installed on these 3,000 clients all over Belgium, and we looked at one typical winter week and their heating patterns to a typical winter weeks. So what you see on the right side of the chart is 9 clusters, and in each of the clusters you see 1 week. So you see 7 curves corresponding to 7 days, and you see the eating patterns. So for instance, the one which is in the bottom right is probably people living, it's actually, I know it, it's people living at the coast that have a second residence, and they are eating mainly in the weekends when they go in their apartment. But what do we do with this kind of clusters? We, for instance, identified that maybe the one showed there, they have a very high variation in their between the lowest and the highest temperatures of the day. Maybe they have a very high correlation between their internal temperature and the external temperature, and so these are maybe the clients that needs a better insulation. And what we try to do, we try to look with all the data that we have and all the customers that have replaced their boiler by let's say a very bad boiler by a very new boiler. Try to show to show them the figures, so to show what they could win in terms of really money by let's say isolating their roof, or putting double glaze glasses, or changing their boiler. So we are working a lot on trying from the data from the smart thermostat and all kind of weather data to be able to automatically assess which clients would benefit from isolating the roof and trying to quantify, okay, this is the cost of the work, this is the cost, the amount of energy that they can save, this is the expected cost of energy for the next 5 years. So we have all the figures to estimate if it's interesting for them to invest in such kind of works. And so we use also this data for this, trying really to have a better understanding of the behavior of the building and see where we can act to improve the energy efficiency globally. So these were a bit two tracks among the many that we are working on today. I wanted to close the presentation by going a bit off topic, and also saying that these were very, I would say, not use cases that are really super exciting or super advanced, but we are also working on a lot of other topics that are a bit, I would say, more exciting on a data scientist point of view, and we are actually, we created like internal Kaggle competitions within Engie, only for Engie employees, to try to increase globally the interest for data science into the employees base, and to try to collaborate and so that people meet internally. And for instance, one of these initiatives, it was a challenge for which we had about 10,000 images that were labeled with the rooftop orientation. So is the roof oriented south, north, east, west, or is it a flat roof? And we were giving the challenge to all the employees within Engie that wanted to try it, to build a deep learning algorithm to try to identify these the orientation of the roof. And we test the results of this algorithm on 4,000 images, for which, of course, the participant didn't have the answer. And actually, we managed, the best ranked employee managed to get a 92% correct recognition rate. So it was quite, we're quite surprised positively by the accuracy that we could reach. Meaning that it was an open question. Are we able to do this with what kind of accuracy? And with this competition, that was a 3-month competition, we validated that it was technically feasible, and the next step is to gather all the 5 or the 10 best ranked employees around the hackathon to try to go one step further and see if we could industrialize a solution based on this idea. And we are launching a lot of these challenges as a way to promote data science internally. So I wanted to maybe it will give ideas to people from other companies here. So that concludes presentation. Hope it was interesting, and I guess there is room for questions.
So yeah, people are thirsty or something.